Imagine a future where thought alone can help heal a damaged body, where the very act of thinking about movement can unlock recovery. This incredible potential is at the heart of how brain-computer interfaces are transforming rehabilitation. Brain-computer interfaces integrate with motor recovery pathways by directly translating brain signals into control commands for external devices or virtual environments. This establishes a new communication bridge, effectively bypassing damaged neural roots or augmenting weakened ones, thereby stimulating the brain to reorganize and rebuild connections crucial for restoring motor function. The fundamental mechanism behind this integration lies in the brain's remarkable capacity for plasticity, its ability to adapt and rewire itself. When an injury disrupts motor control, the brain naturally attempts to compensate, but often inefficiently. BCI systems capitalize on this plasticity by providing consistent, volitional, and targeted neural input. They detect the specific brain activity associated with the intent asterisk to move a limb, even if that limb cannot physically respond. This detected intention then triggers an external action, such as moving a robotic hand or a cursor on a screen, creating a powerful, real-time feedback loop that reinforces the desired neural patterns. This process activates the brain's natural sensory-motor learning pathways. As a person repeatedly attempts to move and receives immediate, positive feedback from the BCI-enabled device, their brain's motor cortex begins to reorganize. These closed-loop systems continuously monitor brain activity, provide feedback, and adapt, which means the brain is constantly learning and refining its control signals. This targeted engagement helps to strengthen existing weak connections, form new synapses, and even recruit adjacent brain areas to take over lost functions, driving significant improvements in motor control. A key concept here is the efferent pathway, which refers to the motor nerves carrying signals from the brain to the muscles. In cases of spinal cord injury, for example, this pathway is often severed. BCI technology bypasses this by decoding the motor intention directly from the brain's cortex, often the primary motor cortex, and then using that decoded signal to drive an effector like an exoskeleton or a functional electrical stimulation device. This creates a sort of artificial efferent pathway, allowing the brain to practice motor commands and receive proprioceptive feedback even without an intact biological connection. Ultimately, the integration of brain-computer interfaces with motor recovery pathways provides a dynamic platform for neurorehabilitation. By leveraging the brain's inherent plasticity and establishing direct volitional control over external aids, BCIs offer a powerful tool to reactivate dormant neural circuits, enhance motor learning, and enable individuals to regain a greater degree of functional independence following neurological injury.